Welcome back to another video. In today's video, we're going to take a look at alkyne reactions. Um, there are many alkyne reactions that can occur. We can turn our alkyne into a vinyl halide, a vicinal dihalide, an aldehyde, geminal halide, alkane, alkylation reactions can occur, so I can actually extend the chain. I can create a transalkene, a cisalkene, a ketone, a carboxylic acid, and some other reactions that we'll take a look at along the way. Okay, so this video is going to be less mechanistic. Believe me, there's still going to be a whole bunch of mechanisms involved, but when it comes to alkynes, showing the actual synthetic route is much simpler, and you'll see what I mean as we go along. Okay, so one of the first reactions we're going to take a look at is going to be how do we actually make an alkyne, okay? And it is an E2 elimination. So let me show you this reaction first, and then we'll break it down together. I have this guy right here. This guy is known as my still bean. And if I treat this guy to make a Br2 in no, not to make a Br2, but I treat it with Br2 in dichloromethane, I will make, and you guys should already know what I'm going to make here, right? I have made a vicinal halide. This is a reaction from the previous video, right? We have done addition of Br2 to an alkene. Okay, this should be no surprise. So why am I showing you this? Because this vicinal dihalide, or dibromide in this case, I can turn it into an alkyne. If I add two equivalents of potassium hydroxide in ethanol, okay, or, if I do it in sodium amide, right, two equivalents of sodium amide and NH3 liquid at minus 33 degrees Celsius. If I either use this or this conditions from my starting vicinal dihalide material, I will get this specific alkyne, okay, which is called diphenylacetylene. Okay, so this is my acetylene, and this is one phenyl, two phenyl, so diphenylacetylene. Okay, so this first reaction is called a double dehydrohalogenation of vicinal dihalide to alkyne. Okay, so why is it a double dehydrohalogenation, and what is the specific mechanism? Okay, so I'm going to omit the mechanism of how we make the vicinal dihalide. You guys should already know that from the previous video. And we're going to just start the mechanism off from when we have the vicinal dihalide. So here's my vicinal dihalide. Boom, boom. There is a hydrogen. Let's show it this way. That's better. And there's again, hydrogen. Okay? So let's say we're using something like potassium hydroxide. Okay? In that case, I have the OH minus. It will come and get rid of this. This will come here, and this will leave there. This, if you recall, is an E2 mechanism. Okay? So a type 2 elimination. And this will get me this product. Okay, the bromine is still here. And I have a double bond now. This intermediate, by the way, is called a vinylic halide. Do not confuse this with a vicinal halide. Two completely different things. This is a vicinal halide where I have one and two halogens that are on adjacent carbons, hence they're called vicinal. A vinyl is anything that is directly attached to an alkene double bond. Okay, so this halogen is directly attached to an alkene double bond. It's called a vinylic halide. So here's a vinylic halide intermediate, and then I will treat this vinylic halide intermediate with another OH minus. Guess what? I will grab this. This will come here. That will leave. And what do you know? I form my diphenyl acetylene. Okay? With the byproducts being two water molecules. Okay, as you can see, one forms in this step and one forms in this step. And the two Br minuses that leave will go ahead and associate with the two potassiums from our KOHs. And they will make 2KBr. Okay? So this is all of my products, okay? And of course, side products. And this is how you make an alkyne. Okay, so double dehydrohalogenation or double elimination, specifically E2, of this reaction. Now, again, the reactants or reagents you can use are either a vicinal dihalide or a geminal dihalide, okay? So if you're curious, here's what a geminal dihalide would look like. Okay, we'll take a look at a geminal halide in a second. Geminal dihalide, but it's essentially and you know, there's hydrogen here and hydrogen there. But this is a geminal. Geminal means that they're both halogens are on the same carbon. Okay? So your starting product for this reaction could be a vicinal or geminal dihalide and a strong base. Okay, so either potassium hydroxide, like we said, in ethanol, or sodium amide in liquid ammonia. You have to use two equivalents of base if you want to generate an internal alkyne, or three equivalents if generating a terminal alkyne. There is no regiochemical or stereochemical variation, right? Both halogens leave the same vicinal carbons, and the triple bond forms between the original halogenated carbons. Okay, so nothing to even worry about there. Now, since we know that a vinylic halide is this intermediate before we get our alkyne, then wouldn't you say that we can actually do another reaction where instead of starting with a vicinal dihalide, I just start with a vinylic halide? Absolutely. So that's going to be the second reaction. The second reaction is just a dehydrohalogenation of a vinyl halide. Okay? And in this case, let's say I have something like this with the hydrogen there. And if I, and by the way, this is an important kind of step to point something out here. A vinylic halide is less reactive, so a strong base is required for this reaction, something like sodium amide, right? We're going to use 2 equivalents of sodium amide in liquid ammonia at minus 33 degrees Celsius. Anytime you use this liquid ammonia here, you have to do it at minus 33 degrees Celsius. And then followed by, and this is step 1, step 2 is followed by an acidic workup. Okay, but again, it's the same kind of E2 elimination. I'm not going to show you, right? Again, if you're curious, it's literally just, well, in this case, since we're using amide, let's show it as such. We'll come and grab that. This goes there, that goes there. Okay, same sort of thing, and we generate our alkyne product. So count your carbons: 1, 2, 3, 4. 1, 2, 3, 4. There you go. And this is your final product. Okay, so remember the chloride leaves from the first carbon. Sorry, from the second carbon, so it's no longer there. The 1 carbon was a methyl, it's still a methyl, and the 3 carbon had a hydrogen, which is no longer there. Okay, And here's my 4 carbon right over there. Amazing. So this is another kind of method of making a um, alkyne, right? You can either do it from a vinyl halide or you can do it from a vicinal dihalide, okay? And again, you can note vicinal dihalide to alkyne and a vinyl halide to alkyne and vicinal dihalide to alkyne shown here respectively. Okay, perfect. So let's cross these off of our list. Now, um, again, for this vinylic halide, right, um, the conditions are at minus 33 degrees Celsius for the liquid ammonia, and the acidic workup is to quench the reaction. And if you want to be specific, you can actually do it with NH4Cl, okay, so ammonium chloride. Now, this elimination is regiospecific because there is only one beta hydrogen available, okay? If you're curious, this is your alpha hydrogen, this is your beta, this is your alpha carbon, this is your beta carbon, and because this is a beta carbon, this hydrogen is called the beta hydrogen. But nonetheless, it's regiospecific because only one beta hydrogen is available. The stereochemistry is not any factor because, you know, the vinyl intermediate or this vinyl product is just a planar product, and so the final product is also linear, so it makes no difference. And the protonation, like I said, it's if you have a terminal alkyne, it's to protonate the acetylide intermediate that forms. In this case, we don't have a terminal alkyne, we have an internal alkyne. And so in that case, the acidic workup is needed to quench the reaction, get rid of any kind of amides that are still present, and perhaps protonate the alkoxide that would get deprotonated throughout the process of the reaction. Okay, again, sodium amide is a very strong base. So yeah. All right. Our next reaction we're going to take a look at is going to be the addition of HX. Now, to an alkyne. So now this is interesting because there's a bit of a caveat with this, okay? And the caveat has to do with, you know, the specific kind of reactant you have. So remember how before we were talking about, in the alkene video, we were talking about carbocations, right? We said we have tertiary carbocations, alkyl, secondary carbocations, and, you know, a primary carbocation, right? Let's say there's like a substituent there. So we said that this is the least stable, this is the most this is the second most stable, and this is the most stable. There are other kinds, for example. If you remember, I said anything that is bound directly to an alkene double bond is called a vinyl. So we could have what we call a vinylic carbocation, okay? This right here is a vinylic carbocation, all right? A vinylic carbocation is very unstable, okay? In fact, this right here, what I'm showing you is a primary vinylic carbocation, and a primary vinylic carbocation is so difficult to form that there's actually no clear evidence that it even exists. Okay, that's how unstable it is. Now, there's definitely evidence for a secondary vinylic carbocation forming, so let's change this to another kind of R group. Okay, so this right here is now a secondary vinylic carbocation. As a general rule, a secondary vinylic carbocation is about as stable as a primary alkyl carbocation, though generally we like to say that this is less stable even than this primary alkyl carbocation. And so depending on the kind of substituent that we start with in this reaction, right? The intermediate that we get, if it's going to be secondary, the reaction mechanism changes. If it's going to be primary, the reaction mechanism also changes. Okay, because remember, a primary vinylic doesn't want to form. So we're going to take a look at the two kind of different avenues that we can go down. So let's start off by taking a look at a generic mechanism. Okay? So how does this reaction work? Well, let me show you like this. Let's say we have this right here. So 1, 2, 3, 4, 5, or, let's do it this way. 1, 2, 3, 4, and boom. Five and 6. Okay, great. So now we have one hexyne. All right. What can I do with this? Well, I can add this HX to it. Let's just say our X in this case is going to be HBr. And I will do HBr in glacial acetic acid. And the product I'm going to end up getting is 1, 2, 3, 4, 5, 6. Between 5 and 6 is going to be a double bond, and over here there's going to be a bromine, and two hydrogens here now. One of them is actually new, and this hydrogen is actually from that one, that HBr. So what actually ended up occurring here? How did this happen? Well, if I add, like I said, one equivalent of HBr, I get a vinyl halide. So if you were wondering in the previous reaction, how is it that we actually create a vinyl halide? Well, there you go. This is how you create a vinyl halide, right? You can take an alkyne and generate a vinyl halide from it. Okay? There you go. Let's take a look at the mechanism. You're going to add HBr, correct? So it is, in this case, it's similar to kind of that alkyne mechanism that we showed, right? You know, the like I said, the mechanism is similar to the alkene addition of HX, right? So we generate this intermediate here, right? Boom, 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 boom. So 1, 2, 3, 4, 5, 6. There will be a positive charge here. There will be an H and an H, and your Br minus will start attacking there, and you generate your product that way. So this is your mechanism, and this right here is my secondary vinylic carbocation. Okay, so you see right here, my secondary vinylic carbocation got me here. Now, if you add HBr even further to this, okay, so this was one equivalent of HBr. If I add another equivalent of HBr, again, in glacial acetic acid still, what I will end up getting is a geminal dihalide, okay? A geminal dihalide. So let's take a look at this. The mechanism is very similar. I add the HBr again. Boom, boom. I generate a carbocation intermediate as per usual. 1, 2, 3, 4, 5, 6. this one already has a Br, already has the H, a third H, and a plus charge now. And so my Br minus is going to add from the top face there, and we're going to get this product. 1, 2, 3, 4, 5, 6. So boom. There you go. I have now, and you can show the hydrogens if you want, but this is now a geminal dihalide. So the trend that I do want you to understand is that if I have an alkyne and I give one equivalent of HX, then I get a vinyl halide from it. If I give a second equivalent of HX to that vinyl halide, now I get a geminal halide. Okay? And you can do this reaction with X being HF, HCl, HBr, but not HI. Okay? Not with HI. All right. Next, let us talk about the reaction very briefly. Oh, let me tell you about the other way the mechanism can go. So the other way the mechanism can go is, let's take this kind of simple alkyne, and we add HBr, another HBr. So this is the other way the mechanism can go, is that the nucleophilic pi bond will remove a hydrogen from this HBr, and at the same time that's occurring, a second molecule of HBr donates electrons from here to form a carbon-halogen bond, developing a kind of transition state, which is depicted by this double dagger plus right there. Developing a transition state that looks like this. I still have my double bond. I still have this H, and boom. So you see how this bond is in the process of breaking. This bond is in the process of being made. This bond is in the process of breaking, and this is in the process of being made. And there's actually one bond missing here. This bond, the triple bond, is in the process of being broken. Okay? Now, as this is happening, a delta plus is forming on this carbon. And a delta plus would be forming on that carbon. But the thing is, the delta plus that is developing is favored on the more substituted carbon. Okay? Because, of course, it's very much so stable there. As compared to the other position. And so the bromine will end up adding here as opposed to adding here. Okay? And so you end up with this product that is our bromine. Okay? So this is the other kind of mechanism. All right? Great. So now let's talk a bit more about our reaction. So again, the mechanistic details include a stepwise reaction by way of a vinylic cation intermediate or via a bridged intermediate. The addition is generally Markovnikov, okay? Because of the fact that these kind of positive charges develop either in this electronic way or there's actually a carbocation intermediate formed, right? Therefore, more substituted position is favored, right? Thus, Markovnikov. Okay. The reactants or reagents, they could be either a terminal or internal alkyne, and HX the condition, one equivalent in order to make a vinyl halide, and a second equivalent if you need to make a geminal dihalide, such as we depicted here. Like we said, it's regioselective, Markovnikov orientation. It's not stereospecific. The triple bond can give a mixture of E and Z alkenyl halides. Okay. There is no acidic workup required, and yeah, that's pretty much it. That's pretty much all I wanted to get out of this reaction. Let's talk about now the addition of an X2. Okay, so let's cross this off of our list. We talk about how to make a vinyl halide now. We know how to make a geminal halide. Okay. Amazing. And, I just crossed off how to get to a geminal halide because, of course, we took a look at that right here, and I crossed off vinyl halide. But I didn't cross off how to go from a geminal halide to an alkyne, but we did mention that this is possible by the same mechanism that we looked at for a vicinal dihalide. Okay, um, so and I've gone ahead and drawn it out here for you, right? If I started out with a geminal product, right? If I, had my geminal dihalide that I made here, but I wanted to go back to an alkyne, it's the exact same kind of mechanism, right? I get that OH, it abstracts a proton, electrons go here, double bond forms, one bromine leaves as a leaving group, second proton gets grabbed, triple bond is forming, and this second bromine leaves, and voila. Okay, so it's extremely similar. Okay. Um, One other thing I would like to mention to you is that while we do say that, okay, we add one equivalent here and two equivalent here, it should be noted that typically the alkyne will react twice to generate the geminal dihalide because after one reaction, there is still a second pi bond left, right? So after one reaction with the HBr, there's still a second pi bond left, so it will react again. All right, so that should be noted for you there. Okay, now we're going to take a look at the halogenation of an alkyne. So reaction number 4 is addition of X2 to alkyne. And this can get us a couple of things. Okay, so this can give us a anti-vicinal haloalkene and a tetrahalide product. So you'll see what I mean here. Imagine this: 1, 2, 3, 4, 4, 5, or never mind. This should just be like this. Boom and boom. So 1, 2, 3, 4. There's a hydrogen at the end. So we have one butane over here. Drawing alkenes is always very annoying for me. If I add X2, in this case it's a Br2 in dichloromethane, okay? Notice the solvent stays the same from an alkene. I will generate a, and let's do this, actually. Boom and boom. I've actually generated an anti-vicinal haloalkene, not alkane, okay? And by another addition of Br2 in dichloromethane, I generate a tetrahalide product. Okay. So there's a Br there. There's a Br there. Br there. And a Br there. Okay, so here's a tetrahalide product with one hydrogen, of course, here, and 0 hydrogens here. Okay, so again, tetrahalide product. Okay, so as you can see, an alkyne can be turned into a vicinal haloalkane or a tetrahalide. In this case, a tetrabromobutane. Okay, and in this case, a dibromo or a 1,2-dibromobutene. Okay, so let's take a look at the mechanism of this. Yeah, so I went ahead and drew out the mechanism here for you. It's extremely similar to that of a um, alkene halogenation, right? So, you get the bromonium ion intermediate forming, right? Except there's a double bond here. Backside attack of this bromine opens up the ring, right? And, once the ring opens, of course, um, another bromination occurs, right? This remaining pi bond will kind of come and add here, right? And, form another bromonium ion intermediate, and another backside attack occurs. And essentially, you end up getting this kind of tetrahalide intermediate. And you might be saying, wait a minute, this, whatever you drew here, looks different from this. And to answer your question, I've written it down here. This is upside down. So if I rotate this or flip it the other way around, you'll notice that the bromine goes up. This will go down. This bromine here will become that, and you get it. Okay, so essentially just flip this upside down to the other side, and you get this. And the reason this works is because this is a planar molecule, because it's sp2 hybridized. So amazing. Now, the tetrahalide is the same. I've just kind of redrawn it here. So yeah, there you go. This is the mechanism for the addition of H2, not H2, Br2. Again, if you add one equivalent, I get the vicinal haloalkene. If I add two equivalents, I get the tetrahalide. The first addition is occurring anti, right? Hence why these two substituents are anti to one another, right? Again, regioselectivity is not really a factor here because you get a fully substituted tetrahalide, right? It's not really any problem at all. Yeah. And so, anyways, that's that. Okay. So this is the addition of X2 to an alkyne to give us a vicinal haloalkene or a tetrahalide. So let's go back to our list here. And let's actually add like this and get rid of that. We've talked about a tetrahalide. We've talked about a vicinal haloalkene. Okay, so we've talked about quite a couple of reactions already. Now, let's talk about number 5, which is going to be the hydration of an alkyne to get us a ketone. Okay? So let's take a look at the kind of reaction here, we are going to do something called mercury 2 catalyzed hydration. Okay, so mercury 2 plus catalyzed hydration of alkyne. So let me demonstrate to you the following reaction. Okay, 1, 2, 3, 4, 5, 6. But I want it to be between 5 and 6, so I will do 1, 2, 3, 4, 5, 6. So again, one hexyne we've seen before. What if I take this one hexyne and in the presence of aqueous acidic conditions in mercury sulfate, and you know why it's called mercury sulfate. We have to use mercury 2 plus because sulfate has that 2 minus charge. Okay, so it's got that boom, O minus, right? So that mercury 2 plus is needed there. Either way, this H2SO4 in aqueous solution, this will give us an intermediate that is what we call an enol. So 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6. There will be a double bond here and an alcohol. So this gives me this intermediate called an enol. What is an enol? Well, an enol means that we have an alkene and an alcohol, so that's the term enol. All right. Now this enol, based off the reaction conditions, which are acidic, tautomerizes. So tautomerizes into something called a ketone. Okay, so 1, 2, 3, 4. Let's do that. And then 5, 6. 1, 2, 3, 4, 5, 6. Between on carbon number 5 is our ketone. And on carbon number 6, there's a methyl. Okay. So you see that I've just received a methyl ketone. Okay? Methyl ketone right there. Now, why does this occur? What is the mechanism behind this? Let's take a look at it. Okay, so there is a tautomerization, and by the way, tautomers are a specific kind of constitutional isomer. All right, so yeah. Okay, the mechanism actually resembles that of oxymercuration of alkenes a little bit. Your reagents are an alkyne, aqueous acidic conditions, and mercury sulfates. Okay? So, by the way, there is a little bit of heating involved, and mercury sulfate, as we mentioned, is your catalyst, right? As the name suggests. Um, so let's take a look at this mechanism. Let's start with a very basic kind of R internal alkyne. Sorry, terminal alkyne. Let's do that instead. Boom, 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 boom. Okay, great. So what's going to happen is we're going to grab the mercury 2 plus SO4 2 minus. Okay, we're going to grab that and make a bond to it. Okay, so now we're going to have our carbon double bonded. We still have our hydrogen, and now we have the mercury. Instead of it being 2 plus, now it's plus SO4 2 minus. Okay, because it's made one bond now. Okay, amazing. Am I missing something? Of course, I'm missing a plus charge, right? There is a carbocation that's formed now. And what is going to happen to this carbocation? Well, a water is actually going to come in here and attach itself to this carbon. And so now I'm going to get R, carbon attached to this OH, H plus, still double bonded to this hydrogen and my mercury plus SO4 2 minus. Okay, amazing. Another water will come and get rid of this. Okay, plus charge there. Deprotonate it, if you will. We will generate an alcohol. Okay, so this is essentially our enol intermediate. We're almost there. Again, mercury plus SO4 2 minus and my OH. Okay, so now we have our mercury containing enol. The question becomes, how can I get rid of my organomercury compound? So to continue the mechanism, I'm going to go over to the next page, but just because I've ran out of space there. But do remember, we had our carbon doubly bounded to this carbon. There was the hydrogen, there was the mercury plus SO4 2 minus, and we had our alcohol, okay? So now the problem was we needed to get rid of this mercury, okay? How do I get rid of my mercury? Well, I can get rid of my mercury by acid, okay? So let's have my acid here. Okay, and actually, let's depict my acid better. OH2 there. There you go. This double bond is going to come here. Pack that. Okay. And actually, at the same time, we are going to, you know, change up here. Remember that we had our OH. Well, this is going to come down, okay, to form this particular product. Boom, boom. I'm just going to switch to line bond because it is so much easier. And C plus, SO4 2 minus. Don't forget this. Don't forget your plus charge. And now we're going to have a OH2 come and grab this guy, and this will come there, and this will go there to fix our charge. And now I will have boom, boom, OH, and show our hydrogen there, show our double bond there. Amazing. So now I have my enol and I have removed my mercury. Okay. Now the question is, how can I tautomerize it into a ketone? And again, this is where our acid comes in, right? So, and again, by the way, I have omitted the hydrogen, but you should know that it's there, right? When we protonated here, there is an extra hydrogen here now. I should, just for the sake of people not being confused. But anyways, so now what ends up happening is that, so what's going to happen is that the electrons that are here are going to come down there, and the electrons here will come and grab our acid. This will occur, right? And we will generate at first this product. H, 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 boom, boom, boom. So this again is the thing we are going to use. And now an OH2 will come by and pick this guy up, and voila. Well, actually, we don't need to do that. Um, and that generates us our ketone. Okay? Boom, 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 boom. Okay, so that's my methyl ketone there. And there you go. Okay, there you go. That is the tautomerization occurring under our acidic conditions. So that's a very long mechanism for this, but it is important to understand that mercury catalyzed hydration of an alkene, right? As the name suggests, we hydrate, we add a water, right? So that means we must be getting an OH somewhere on the chain. And the thing is that OH under this specific acidic conditions will tautomerize into giving us a ketone. Okay, and so um, we have now talked about the production of a ketone. Okay, which is impressive. So now you know how to make a ketone. And that was reaction number 5. Okay, that was reaction number 5. Something important to understand is that if I have an internal alkyne, so that mechanism was done by a terminal alkyne, but if I have an internal alkyne, okay, versus a terminal, what is the difference? Well, an internal alkyne under aqueous acidic conditions in mercury sulfate gives me a mixture of two ketones. All right, so internal alkynes produce a mixture of ketones, whereas a terminal alkyne gives just a methyl ketone, just like we saw, right? It gives us that methyl ketone because of the mechanism. Whereas again, this gives me one ketone and a second ketone. This gives me a methyl ketone. Okay, great. So again, the enol intermediate in this reaction tautomerizes to a ketone. Depending on if it's internal or terminal, right? You might get 2 or 1. The reaction is regiospecific, right? It's Markovnikov. Remember, the hydration adds the OH to the more substituted carbon. If you don't remember, here it is. This OH2 is going to add to the more substituted carbon. This R group is another carbon, whereas if the positive charge added here and the mercury sulfate was here, then the positive charge would have been less stable there, right? So again, it is Markovnikov. Reaction is not stereospecific. The addition across the triple bond can be syn or anti, but the final ketone has no stereochemical center, so it doesn't really matter. And there are several steps involved, okay? There is forming a complex with the metal, mercury. There is nucleophilic attack of the water. There's a couple proton transfer steps. Then there's a demercuration step, which is over here. And of course, the tautomerization steps down there. There is no acidic workup required. It's part of the reaction mixture, right? Because it's aqueous acid. And yeah, so this is how you make a ketone from an alkyne. So that was reaction number 5. Reaction number 6 is going to be hydroboration oxidation. And in a hydroboration oxidation, again, I get a aldehyde. Okay? So unlike before, where I actually got a OH or an alcohol in alkene, in an alkyne it's completely different. I don't get that. So let's take a look at this reaction. It is alkyne hydroboration oxidation. Perfect. Now, this reaction type is very interesting. I'm not going to show you the mechanism for this because it is rather complicated. So um, we are going to skip that. But, you know, the hydroboration step is extremely similar. It is very concerted. Um, a couple of notes are important with this specific reaction. So one thing is, and again, you know, we're gonna take a look at this, but if you have an internal alkyne versus a terminal alkyne, the outcome you get is going to be a bit different. So let's take this internal alkyne. How many carbons do I want? 1, 2, 3, 4, 5, 6 alkyne. Okay, so 1, 2, 3, 4, 5, 6. And I want it to be an internal, so 1, 2, third and fourth carbon is where the double bond will be. So 1, 2, 3, 4, 5, 6. Okay, perfect. So this is my internal alkyne. And let's make another one with a terminal alkyne. And let's make that a bit simpler. Let's make it 4 carbons. So 1, 2, 3. And I really hate alkynes. There we go. All right. So this is simpler. 1, 2, 3, 4. Okay. So here we have an internal versus a terminal alkyne, and we're going to perform an oxidation of both of these guys. So let's do this right here. Remember, we will use hydroboration oxidation. If you remember, we used a BH3 in THF. But here's the kicker. We don't actually use borane. Why do we not use borane? Well, the thing is, terminal alkynes specifically often react twice with BH3. Okay, so let's write this. So it's completely fine to use BH3 with an internal alkyne. Okay, but a terminal alkyne reacts twice with a borane, and that leads to a complicated, you know, side product mixture. And in order to avoid this, we use what we call a sterically encumbered dialkyl borane. Okay, so BR2, dialkyl borane. And examples of this include things like dicyamylborane or dicyclohexylborane. And if you're curious, dicyamylborane is as such. So here's my borane. It's bound to that H group, right? There we go. And so you can certainly see dicyamylborane here is very sterically encumbered, and dicyclohexylborane, which is this one, boom, 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 and okay, so this is dicyclohexylborane, and dicyclohexylborane, dicyamylborane. You can see that they're both sterically encumbered, and so this sterically encumberedness of the dialkyl boron forces the boron here to react with the less substituted carbon and to give a non or anti-Markovnikov product. And the big bulky groups also prevent side reactions. Okay, so this is important. And again, it's important to understand that in general, alkynes will react with a borane to give us a vinyl borane intermediate. And the vinyl boranes, upon reaction with hydrogen peroxide in slightly basic conditions, can be oxidized into an enol, which will then tautomerize to give, again, either a ketone or an aldehyde, just as before. And notice how, beforehand we had tautomerization occurring in an acidic condition, acidic medium, whereas now we have tautomerization occurring in a basic medium. Okay? So if you remember, um, when we had an alkyl borane forming from our alkene, right? So if I reacted my alkene with a BH3, I would form a what? An alkyl borane. Okay, so something like this. BH3. And upon oxidation, it would generate me a alcohol. But for an alkyne, when an alkyne reacts with a borane, it generates me a vinyl borane intermediate, and upon oxidation, the vinyl borane gets me a enol, and the enol, instead of staying as this alcohol form, will tautomerize into the corresponding ketone or aldehyde form, depending on the substitution pattern of your product. Okay, so this is important. Now, these are the couple notes that I wanted to mention about this reaction. So now, let's get into it. So, if I have the internal alkyne, what is going to be my product? Well, I'm going to get my vinyl borane intermediates. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. With the double bond being at the 3 and 4 position, the borane being added here. Again, remember, it's perfectly fine to use a BH3 for internal alkynes. And of course, this would be H2 and H over there. And, it adds in a syn fashion. Okay? So the BH adds in a syn fashion. So, it is a sorry about that. This diagram is wrong. It adds in a syn fashion, so this should be 1, 2, 3, 4, 5, and 6. And so this is where the other hydrogen is adding. There you go. So this is my intermediate, because this will always add in a syn fashion. And upon oxidation with hydrogen peroxide and OH minus, basic conditions, right? And a little bit of water, whatever have you, you end up getting, and let's change the direction of the arrow. You end up getting an enol intermediate, right? So boom, 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 boom. You have your enol intermediate, and that enol intermediate will, of course, tautomerize into, in this case, what? A ketone. Why a ketone? Because there is a carbon on this side and there's a carbon on that side, and so it will give us a ketone. if you want to kind of see, there you go. That is our corresponding ketone. Great. What about the use of an encumbered, sterically encumbered borane in this case? So, well, you can abbreviate this as um, BR2. Okay. If you want, there are specific abbreviations. So, for example, cyamyl is this. This is dicyamyl. No, not cyamyl. This is dicyclohexylborane. And cyamyl, I'm sure, has its own abbreviation. But either way, we're just going to be generic and say HBr2, not BR, HBr2. There we go. Again, in THF. What is that going to get me? Again, it adds in a syn fashion. So 1, 2, 3, 4. BR2 and H over there, adding upon oxidation with hydrogen peroxide and sodium hydroxide and water. That gets me what? Gets me boom, boom, boom. The enol form. And in this scenario, I'm getting that enol form and oh, sorry about that. Absolutely sorry about that. This is wrong. And this is a great opportunity. Anybody tell me why this is wrong? Because a borane will always add to the less substituted carbon. In this case, it didn't really matter because it is a symmetrical alkyne, right? There's 6 carbons, so and no substituents, so this is good. But this one, it should actually be the reverse. Hydrogen here and Br2 there. Br2 hydrogen. Of course, the OH is going to replace the Br2. And because there is no extra carbon there, and there's only 1 carbon here, when we go through tautomerization, we will get the aldehyde form. Okay? We will get the aldehyde form. All right. So let's go through this reaction. Like I said, alkyne is required, borane is required. If you're looking at a internal alkyne, if you're looking at a terminal alkyne, a bulky dialkyl borane such as dicyamyl or dicyclohexyl borane is required, and in THF, of course, and both of them are followed by hydrogen peroxide and hydroxide and water. So that is that. Next is going to be the formation of that enol intermediate, which will then tautomerize to a ketone or an aldehyde. For a terminal alkyne, you will always get an aldehyde. For an internal alkyne, you will always get a ketone. The reaction, of course, is regiospecific, being anti-Markovnikov or non-Markovnikov, because the boron always adds to the less substituted carbon. It is stereospecific because the BH adds syn across the double bond. And a bulky dialkyl borane, like we said in the terminal alkyne scenario, prevents double addition. So it stops those messy byproducts. We said that the oxidation is going to replace our boron with our hydroxyl, and tautomerization will yield us the carbonyl compound. Okay. So again, we're not going to take a look at the mechanism of this. This is rather, uh, you know, rather difficult. Um, so yeah, we won't be taking a look at the mechanism. Uh, Actually, you know what? We can take a look at the mechanism very briefly. Um, again, let's just say we have something like this, right? Um, that's terminal. Um, the borane will, of course, position itself as such. Well, sorry, not terminal. Not terminal. There we go. The terminal is just going to make it harder because of the drawing of the dicyamyl, but you guys understand um, that this bond will come and grab here. And I should probably instead just kind of flip this around. That would make it easier. H, B, H, H. There you go. So that comes and grabs there. That comes and grabs here. Okay. Um, and we have that kind of intermediate there that will form. And, now we have our boom, 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 kind of BR2 and H, right? Remember, this was a extra carbon if it's not clear. So um, uh, let's just show it like this and count your carbons. 1, 2, 3, 4, 5. As such. Remember, which one of these two is the least substituted region? This or this? Obviously this one, and so he will come and add there. This guy, again, let's count our carbons. 1, 2, 3, 4, 5. Okay. So that hydrogen was the one from the borane. This is now here. Amazing. Great. Now let's keep going. Remember, we have now added this here, syn addition, right? I'm not going to show you how the hydrogen peroxide is kind of activated, but you should already know that, right? We covered it in the last hydroboration and oxidation mechanism, right? So we know there's water here, of course. We know that we have the OOH, and this is negatively charged, of course, and he will kind of attack our borane, attach to the borane, right? And boom, boom, boom. With our BH2 is now attached to it, a OOH. Okay. Same with the hydrogen there. We now have electrons from this region going to our oxygen, which now comes here. So that entire thing will, switch, right? Just like we showed before. This portion will leave, and this will now be attached to this bond, and the BH2 will be attached to the O. So let me redraw for you. Boom, boom, boom. See, it's bound to an oxygen and a BH2 and an OH minus. This is the part of that. This will come here. This will grab that. Okay. Next we will, and this is the part that's a little bit different because now we have this negatively charged kind of oxygen. Okay. And, you know, this negatively charged oxygen will go ahead and attack a water. All right. Which will form this. Uh, Again, don't forget our hydrogen. Okay. Um, so now that's the enol form. All right, so this is my enol. But it is important to kind of understand that uh, and from here, what we will do is we will do this. Boom. And you know what? I'm just going to do a shorthand mechanism where we essentially form this. Boom, boom, boom. And this negative charge will grab that, and voila, we have got ourselves a final alcohol product. Not alcohol, aldehyde product. And so you can see that in this case, because it was a terminal alkyne, we got an aldehyde. And again, in reality, this should have been R and R, right? And R2 and R2, R2 for you there. Okay, so that was a keto enol or aldehyde enol tautomerization under basic conditions, as we just saw, right? And that's the mechanism. But I do want to go back, all right? This has been a very long, kind of winded explanation for all these, but I do want to make sure you guys understand that we now know how to make a ketone and we know how to make an aldehyde, which is right over here. We saw how to make a ketone from before, right? We had mercury catalyzed hydration of my alkyne. That gave me a ketone, right? By ketoenol tautomerization. And we can make a ketone or an aldehyde from a internal or terminal alkyne by way of hydroboration oxidation. Okay? So again, many ways of doing things, and we still have a couple of more left. Okay? Trust me, this one will be kind of much more easier. 7, right? Reaction number 7. So reaction number 7 is going to be the reduction of alkynes, right? So we talked about oxidation. Now it's time to talk about the reduction of alkynes. You know, this is referred to as a, we've already seen this before, catalytic hydrogenation, or reduction of an alkyne to an alkane. Okay? So mechanistically, we have this bad boy right here. Okay? Internal alkyne. We will add H2 to it. Okay, by way of that, palladium on carbon or platinum dioxide. whatever. It's a surface-mediated addition of two equivalents of H2. Okay. So first things first, you will get the alkene. Okay, remember this is 1, 2, 3, 4. So 1, 3, 4. And another H2 is added, and you get 1, 2, 3, 4. So notice right here, two equivalents of H2 are added, okay, to get a fully saturated. Now, normally we can't actually stop at the alkene, okay? Once you add the H2, it fully goes on. The alkyne fully goes on to become an alkane, all right? And that's that catalytic hydrogenation. So this is catalytic reduction or hydrogenation of alkyne. And it's surface mediated. We said it's done on palladium on carbon. So triple bond is fully hydrogenated to a saturated hydrocarbon. Both pi bonds are reduced. No stereochemical or regiochemical considerations even apply here. The reaction simply just adds 4 hydrogens and the product has tetrahedral geometry. Now, what we can do is do something like how the question is, how can we stop at the alkene? Right? That is the question. And the answer to that question is partial hydrogenation. However, this is the important part. Partial hydrogenation gives you a cis alkene. Okay? So partial hydrogenation gives you a cis alkene. So example, instead of, and let me do this. Okay? Instead of using a regular palladium on carbon, I use something called Lindlar's catalyst, which is essentially palladium on carbon, but it's just kind of poisoned, if you will. So, like I said, it's essentially kind of poisoned. Because usually, with the palladium on carbon as the catalyst, hydrogen adds to the alkyne and to the intermediate alkene, giving us the alkane product. Okay? And it is impossible to stop at the alkene reaction unless you use what we call a Lindlar reaction. And a Lindlar reaction, like we said, or a Lindlar catalyst, is essentially a poisoned catalyst that stops and gives us the alkene product. So in this case, a Lindlar is palladium on carbon treated with PbSO4 and quinoline. Okay. You can also, use barium sulfate or PbSO4 like we already talked about. But Lindlar catalyst is a finely divided palladium metal that has been precipitated onto a calcium carbonate support and then deactivated by treatment with lead acetate, which is PbSO4, and or PbSO4 and quinoline and aromatic amine. That's what quinoline is. But either way, the catalyst is treated to make it less active. And no over reduction occurs. And thus we stop at the alkene. Now you should note that because this is a surface catalyst reaction, and that both of the hydrogens are added to the same face, the reaction is stereospecific and you only get the cis alkene. Okay? Because again, it was a syn addition of both hydrogens to the same face of the molecule, so it will be a kind of cis alkene. So now we know how to make a cis alkene, right? By using a Lindlar's catalyst and doing a partial hydrogenation. So if I do this exact same reaction, but instead I use Lindlar, then I will get this cis alkene only, and the second reaction won't occur to give me the alkane. All right. If I wanted the alkane, then I would just use a regular palladium on carbon, not my Lindlar's catalyst. Okay. Amazing. Now, what if I don't want the cis-alkene? You know what I mean? What if I don't want the cis-alkene? What if I want the trans-alkene? Well, in that case, I have to do another reaction. So this reaction, and I'm going to group all of these together in number 7. This reaction is called dissolving metal reduction. So dissolving metal reduction. And dissolving metal reduction is a radical mechanism. So it occurs stepwise via a radical anion and carbanion, and it has anti-addition occur. Imagine we have again this internal alkyne. If I treat it with lithium and ammonia, I will get, and by the way, this ammonia is at minus 78 degrees Celsius. You could use lithium or sodium in this reaction. And this is liquid ammonia, don't forget. This gives you my transalkene. So 1, 2, 3, 4. This gives me the transalkene. Okay. So dissolving metal reduction gets you the transalkene. Catalytic hydrogenation with the Lindlar catalyst of an alkyne gets me the cis-alkene. Okay. Perfect. Now, oh, by the way, why are we doing this ammonia at minus 78? Because that's the boiling point of ammonia, right? So we want it to be in a cool environment since we're working in liquid ammonia. Now, I will show you the mechanism of this one. I will show you the mechanism of dissolving metal reduction. So let's take this guy over here. Let's start with him. It is a radical-based mechanism, so we have an elemental sodium or lithium. In this case, I will use sodium. So remember, usually when I put this symbol, that means elemental. Elemental sodium will come here, and it will, remember, this is a radical-based mechanism. Okay. There you go. We'll donate this kind of electron there, and I will generate this intermediate with a radical here and a carbanion here. Why is there a carbanion here? Well, that's because of this. Okay. So now I have a radical vinyl anion, or vinyl radical anion. A vinyl radical anion is very basic. It's extremely basic. So it will attempt to deprotonate our ammonia. Okay. And that will generate us this. Boom. Now hydrogen's added to it, and still that radical, okay? So once we get a neutral vinyl radical, which is this, it quickly adopts the trans conformation of substituents due to steric hindrance, okay? Remember, a cis conformation has lots of steric hindrance, but a trans conformation does not have much steric hindrance, okay? And so now another sodium is going to come in, and it will kind of, do that. Although, if you would like, we could actually show it like that. and that would produce to us another carbanion. This time it's just a vinyl anion. There's no longer a radical, right? Because we solved that problem. So again, it's a vinyl anion. It's very basic. What does it do? It will deprotonate our ammonia. Let's bring him closer. And of course, H2N. Of course, those will go there. So now I have boom, boom, boom. I'm finished. I have this, and I have this, and I have the transalkene. And one of my byproducts is, of course, sodium NH2 minus. Okay, perfect. Okay, so again, you do note this is a radical-based mechanism, stepwise via a radical anion and a carbanion, and there is anti-addition of my substituents occurring. I do want to, again, I do want to point out, once we get here to this neutral vinyl radical, you know, the trans stereochemistry is established because the less hindered trans vinyl anion is formed in this region from the vinylic radical, and then the vinylic radical undergoes rapid cis-trans equilibration, but the vinylic anions equilibrate much less rapidly. Thus, the more stable transvinylic anion is formed rather than the less stable cis, and is protonated without equilibration. Okay? So, this is the important part. Okay? But again, I do just want you to remember that there are three kind of reductions that we took a look at. One is a complete reduction from an alkyne to an alkene. Next is a catalytic poisoned reduction by way of Lindlar's catalyst that gets you the cis-alkene. And the other is the dissolving metal reduction that gets you the transalkene. In this specific conditions, lithium or sodium metal, liquid ammonia at minus 78 degrees Celsius. Okay, so again, these conditions do matter. And you know, in other words, you could say instead of trans, you can say this is the E-alkene as well, and you can say this is the Z. Remember, I like to remember that Z is kind of like for same side, and then E for E cross. All right, E cross one another. We are almost done with alkynes and their reactions. So let's go ahead and cross off stuff from our list, right? We have two more reactions I want to show you. So we talked about how to make an alkane. We talked about transalkene, cis-alkene. Really, there's two more reactions left. One of them is going to be alkylation, and I'm going to show you how to make a carboxylic acid. So, if you remember, I told you that we're going to use our good old friend oxidative cleavage. So reaction number 8 that I do want to show you is oxidative cleavage of an alkyne. Now, the thing is, with these reactions, they don't really occur to an appreciable amount. Okay, so reactions of ozonolysis and acidic permanganate with alkynes are often very low yielding, and they're very impractical. And so they're mentioned for completeness, but they don't really occur to, again, an appreciable amount. But we will kind of, mention them nonetheless. Again, we won't take a look at the mechanism. Just understand that if I have an internal alkyne, Why am I writing this down? If I have an internal alkyne and I use either KMNO4 in acidic conditions or ozonolysis, I will generate a carboxylic acid and another carboxylic acid. And again, this is an internal alkyne. 2 carboxylic acids are achieved. So now you know 2 methods of making carboxylic acids, from an alkyne or from an alkene. Okay, and the alkene one also consisted of ozonolysis. Or sorry, KMNO4, not ozonolysis with alkenes. Okay. If I use a terminal alkyne will still give me a carboxylic acid, but it will give me a CO2 just like before with KMNO4. But ozonolysis does the same thing in these guys as well. So R and CO2. Okay. So that's what I wanted to show you there. Again, oxidative cleavage, you know, it's ozonolysis followed by a hydrolysis, or it could be permanganate oxidation. Remember the conditions for this, right? You did this in dichloromethane, and the second step involved zinc and acid, right? KMNO4, what did we do KMNO4 in? Let me check. KMNO4 was done with acid. Yeah, acidic permanganate. Yeah, acidic permanganate. Okay. So, the reaction is often heated. We said that the internal alkynes give 2 carboxylic acids. Terminal alkynes give a carboxylic and CO2. There's no stereochemical or regiochemical considerations. Triple bond is just simply cleaved to carbonyl fragments. Ozone or permanganates give us a carbonyl fragment from the triple bond. Amazing. Okay, now the final reaction that I want to work with you is, and this is the one that is, you know, a little bit difficult, is first the formation of an acetylide anion, and next reaction would be alkylation with acetylide anions. Okay, so let's take a look at this. First things first is we have to understand that in order to form an acetylide anion, we have to undergo an acid-base reaction. So you need a terminal alkyne for this. Okay. The reason you need a terminal alkyne because you need a proton, an sp hybridized proton, which is quite acidic. All right. So you need a strong base here. You could use a couple of things. One of them is sodium amide. The other one is NaH. And the other one is N-butyllithium. Okay, so you could use a couple of strong bases here, but for the mechanism, we're going to use, you know, this dude here, sodium H2N minus. And we're going to cleave off that proton. I should show that. And that's going to form us a acetylide anion, okay, which is highly basic, highly basics, and the conditions are, either in liquid ammonia or THF, right? You want it to be anhydrous, okay? You don't want it to be water involved because that'll kind of get involved in the formation of the acetylide anion. But the acetylide anion is really important, okay? There is no stereochemical or regioselective consideration. This is an acid-base deprotonation. The terminal alkyne is relatively acidic because of its sp hybridized carbon, very high S character, stabilizes the anion, right? And so they are relatively acidic. But what can we do now that we have generated this acetylide anion? Well, the acetylide anion can do a couple of things. It can participate in an alkylation reaction, and this is the first reaction we're going to learn about extending the carbon chain, okay, for at least a linear or whatever compound. But it performs an SN2 mechanism, okay, an SN2 reaction, alkylation by what's his name? Acetylide anion is an SN2 mechanism. By molecular nucleophilic substitution, you need an alkyl halide, okay? Preferably a primary alkyl halide because otherwise it won't be able to undergo an SN1 reaction. An SN2 reaction. So watch. I'm going to get hydrogen, 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 and bromine. And I have my acetylide anion, right? This is a primary alkyl halide. So primary alkyl halide. We should know how to make these primary alkyl halides from the previous video, right? Addition of an HX to my alkene, okay? Would get me kind of something like this, right? If I go back all the way up, electrophilic addition of a HX to an alkene would get you a alkyl halide. Okay, now in this case, this was a what? This is a secondary alkyl halide. All right, we need a primary alkyl halide. So that's important. Primary alkyl halide definitely required for an SN2 reaction. And this will leave. And now look at that. We have added this extra carbon to our chain. Like that. Right? Before it was 1, 2, 3. Now we have 1, 2, 3, 4. And these are the 3 hydrogens. There. Perfect. And of course, if you want, sodium's involved here, and so we would make a sodium Br electrostatic interaction. Okay. The SN2 attack of the acetylide anion on a primary alkyl halide proceeds with inversion of the configuration of the electrophilic carbon if it is stereogenic. So the reaction is stereospecific. Don't worry about why right now. There's an entire kind of reason behind this. We'll get to it when we talk about displacement reactions. But SN2 is stereospecific. It is regiospecific as well because the substitution occurs at the terminal carbon of the acetylide not, you know, here or here, right? It has to occur there. What else? Um, yeah, I think that's it, right? Again, nucleophilic carbon on the acetylide attacks the electrophilic carbon of the alkyl halide and displaces the leaving group in one step by way of a backside attack. Um, yeah, that's pretty much it. That's pretty much it, right? So we have now talked about alkylation as well, and this. Okay, so many different reactions covered here today. Um, and I do want to clarify confusion here. You can't. A primary alkyl halide is it's just that you can't. Well, we haven't learned a reaction to make a primary alkyl halide. We've learned a reaction to make secondary, tertiary alkyl halides, but not a primary alkyl halide. Okay, so a primary alkyl halide is just something that you would have to include as a reagent. Okay. But anyways, let's go ahead and give our summary as per usual. So how can I turn an alkene into an aldehyde? Well, we have learned multiple methods of turning an alkene into an aldehyde, right? You can either you can use hydroboration oxidation of a terminal alkyne, right? Hydroboration oxidation of a terminal alkyne that would give you the aldehyde, or that's it. That's it. So hydroboration oxidation of a terminal alkyne. So let us write that down for ourselves. Hydroboration oxidation of a terminal alkyne. Actually, you know, I'm not going to write it down. So again, with the aldehyde, it is hydroboration oxidation of an alkyne terminal. Alkyne generates me, in THF, by the way, generates me the aldehyde. How do I get a ketone? There's two ways to get a ketone. One of them is by hydroboration oxidation of an internal alkyne, as we saw here. The other one is a mercury catalyzed hydration of the alkyne. Okay, so the first method is with mercury 2 plus. The second method is with hydroboration oxidation. And over here, we're going to write BH or Br2 for ourselves. So we know that it's that. How can we make a carboxylic acid and CO2? Well, a carboxylic acid and a CO2, you can make a carboxylic acid from KMNO4 and ozonolysis. And in fact, you make carboxylic acid from KMNO4 and ozonolysis of both internal and terminal alkynes. But with internal alkynes, you get 2 carboxylic acids, whereas with terminal alkyne, you get 1, and you get 1 CO2. Okay, how can I make a cis-alkene? With a cis-alkene, you need to use a Lindlar catalyst. For a transalkene, you need to use dissolving metal reduction. So dissolving metal reduction. Alkylation, you need to use an acetylide ion and a primary alkyl halide. You know, maybe secondary, but primary alkyl halide is best because it has less steric bulk for that backside attack. Alkane is a full-on reduction with palladium on carbon. Now comes all the weird kind of halides. So how do I make an alkyne from a vinyl halide? Well, remember it's a double elimination. You need, and this is important, it's a vinyl, not vicinal. Vinyl halide indicating that it is a halogen attached directly to a double bond. So we will use two equivalents of sodium amide in ammonia. Okay, and that's an elimination reaction with acidic workup step involved. How do I go from this to a vinyl halide? Well, I will just add HX. Okay, if I add HX, I will have a vinyl halide. Again, one equivalent of HX I should add. Because otherwise, if I add a second one, I get a geminal dihalide, okay? And, geminal dihalide. A geminal dihalide is two HX's, two equivalents of HX. How do I go from a geminal dihalide back to a vinyl halide? Well, the same way you do that from a vicinal dihaloalkane. You do that by a double elimination by using 2 KOH and uh, uh, man, it's KOH in, because it is an elimination step in ethanol. There we go. In ethanol, it is an E2 elimination. Same thing with the vicinal dihaloalkane. We've already kind of gone through the mechanism of this. 2KOH in ethanol. Like we said, you could use sodium amide in liquid ammonia at minus 33 degrees Celsius, but not necessary, okay? So these are all of the reactions we have to know for alkyne reactions. I'll see you in the next video when we start talking about reactions of organohalides. All right. Yeah. Final word that I want to mention is that you can actually make a terminal alkyne from acetylene. Okay? And internal alkynes can be synthesized from terminal alkynes. Okay? How, you may ask? Well, by just reacting it with another kind of RCH2. So if I have this terminal alkyne here, right? If I treat it with sodium NH2, right, that would kind of turn it into an acetylide anion. And I attack it to an R prime CH2Br. Guess what? The Br leaves, and I end up with, boom, that CH2 R prime. And now you can see I have synthesized an internal alkyne from a terminal alkyne. Okay? So that's important. The other thing is that the reason why we always use primary primary alkyl halides is because they are the best electrophiles for SN2 reactions because, again, of the fact that they are very less sterically hindered. But a secondary and tertiary alkyl halide, they tend to form elimination reactions and specifically E1 elimination products, okay? So, like we said, acetylide anion is a strong base. And so if we have something like this, right? Boom. Okay. And I add this to my acetylide anion. What's going to actually end up happening is that I'm going to abstract this proton, do this, and get rid of that. Okay? And so I'm going to get an elimination product from this. Um, and so for this reason, we only use primary alkyl bromides and an alkyl iodide. And we don't use alkyl chlorides because they're a really terrible leaving group. Um, and secondary and tertiary alkyl halides are not used. Okay, again, we'll discuss this in a bit more detail later, but not really kind of useful. Okay. All right, so that's that.